Uh, Hello, everyone. Welcome to our blockchain speaker series. I'm excited to have Alex Stokes joining us. And today he's from Ethereum Foundation. He had a very nice career trajectory. I would say perhaps an unusual one, which is probably a good fit for blockchain as well. So he had his degree in chemistry and computational science from Princeton. And then from there on, he really got into decentralized application, governance, and Ethereum, and now he's part of the Ethereum Foundation. So today he's going to talk about crypto economics, and in particular, how do you build the application in this new exciting era? So with that, please take it away.
Great, everyone. Yeah, definitely. I fell down the rabbit hole. Okay, so let's see. So yeah, you all have this series on blockchains and all these cryptocurrencies and stuff. And so today I'm going to talk about one little piece of that, which is essentially you might have heard this term dApps, these decentralized applications. So let's see, I guess we'll just get into it. So I haven't done one of these remotely on Zoom. So this will probably be far more valuable for you if you ask questions as we go. So if something isn't clear, just stop me, interrupt me. The signaling, I'm not as sure about. I have this chat window here. I see someone said yes to my earlier question, which is very helpful. So maybe ping me in the chat, or I think there's like a raise hand feature. Get my attention, and I'll try to pay attention.
Yeah, and if you miss anything, don't worry, I'll speak up. And also, again, in the past few sessions, it worked well. I mean, when people just open up their mic and ask, and I think having that informal conversation is just perfect. So let's make it as much as possible into a real setting that we're kind of sitting together and ask questions and get excited. And yeah, so let's
great. Okay, there's definitely a lot to talk about. So many things to be excited. I was like making these slides earlier, and I was just like, I hope all of you here, you understand. At least I hope that you can sense my excitement and it comes across. So by the end, you're also very interested and intrigued in what's going on. So, okay, so who am I? There is a nice intro already. I'm Alex Stokes. Ooh, can you see my cursor? That would be nice, actually. Oh, anyway, not important. Wait, can you?
Yes, we can see it.
Great. Okay, thanks. Everyone's responding. This is excellent. Okay, so, right. Okay, so this is my GitHub, Twitter, Medium handle, like pretty much any platform. If I have an account, I try to grab this handle. So if you want to reach out to me, that's a great way. Like the professor said, yeah, research and development at the Ethereum Foundation. So I'm focused particularly right now on blockchain scalability. And I know there's a session later, maybe in like a couple weeks ago. You probably, well, I'm actually not sure how much you guys are embedded in the space, but if you've been following a bit, you've almost certainly heard about this. Essentially, the Ethereum that we're about to look more at now, the Ethereum we all know and love, doesn't go as fast as we want it to. So ideally, it would be able to handle many more transactions per second than it does today. And I'm going to try and leave some time for questions at the end. And so maybe we'll, if you want me to talk more about that, I can. But either way, I'll say that for the later discussion. I believe Preston is going to be speaking to you. He works on one of the clients, so that'll be great. Yeah. Anyways, yeah, and then also I'm not sure if I've had anyone frame it as, I've had an interesting trajectory, but that's definitely what has happened. I studied chemistry in undergrad. It's pretty much self-taught, all of my computer knowledge, but I just became obsessed with these types of technologies. And yeah, I've been like full-time in the crypto space since 2017, and now it's like all I think about, and it's great stuff. Again, I'll try to impress upon you how much potential and opportunity there, and you'll hopefully understand why, I see it in the way that I do. Okay, but concretely, just for today's class, what are we trying to do? I hope at the end of this, you'll like have some sense of what a dApp is, because it's maybe a confusing term, especially if you're new to all of this blockchain and crypto and these decentralized ledgers and all of this. Why are dApps Solidity? What does that have to do with this? I believe the next session after me is, was it Kevin? I forget who, but either way,
That's
one
Kevin's
of the
gonna
truffle
talk about, yeah. Kevin's gonna talk about truffle. Yeah.
Right, exactly. So one of the truffle team members is going to speak about that, and like truffle is a development framework for Solidity, which again, an hour from now will make a lot more sense to you. Anyways, well, we'll get to Solidity. I'll just, that's one of the goals for the talk. And then yeah, just generally, how does Ethereum fit into all this? So here's like a brief agenda. We'll start sort of like high level, like why does anyone care? What is this stuff? What is it? We'll kind of drill in a little bit more deeply into, okay, what are these dApps? What are some examples of dApps? We'll look at the EVM and then Solidity itself, which are sort of, these are like the technical implementations of these programs on the Ethereum blockchain. And then, yeah, if we have time, we'll look at some code for different smart contracts and try to get our hands dirty with some of this stuff. So the first question, right? Like, why the hype? Like, why are you here? Why does anyone care? And this is like maybe a little pithy, but essentially here's like a nice metaphor for us. The internet did for information what blockchains may do for value, and like arguably already do, which is essentially, it's like kind of crazy when you think about it, that they're just going to let anyone on the internet, and then you can now talk to anyone else all over the world, right? Like as long as you're connected and you have the right protocols, then you can talk and you can exchange information. And that's like actually like, it's like mind blowing, at least to me. So similarly, with all this crypto stuff, we hope to do a similar type of thing with this like abstract notion of value. So we have this abstract notion of information where now, I can send you tweets, I can send you, messages on WhatsApp, I can do all this stuff. Now what we want to do is basically have like some digital notion of value that we can move across the internet. And perhaps we'll get into a little about why we can do that before, and what is so new about this stuff that lets us do it now. And the way to understand this, again, this is like very high level, and I imagine you've already covered some of this previously, but essentially, at a high level, like we'll talk about what is money, and there's like a whole history here. If you're interested in this stuff, I encourage you to dig in. Basically, right, we can say money is a way to transfer like some chunks of value. So value already is like pretty abstract, but it's sort of the thing where where you see it. And basically, if I do some work, maybe someone thinks that I should be rewarded somehow for that work. So now we need a way to like sort of manipulate that value, or at least it lets us do more in society if we can. So these tokens or these chunks are like things we generally call money. And like across history, there have been a variety of like instruments or like currencies, these different instruments of money. So some examples are these like cowrie shells, which like instead of dollar bills, like literally they would trade like shells, right? Like seashells. Another famous example are these rye stones. So from the Micronesian island of Yap. Basically, they're these huge stones, like meters across in diameter. But essentially, they're like, you could imagine like one huge stone is maybe like, $1,000 or something like this. And then they actually had a very intricate system of debts where they could essentially subdivide. And again, all sort of like abstractly, they could subdivide the stone and the value attached to the stone, and they would track, who in the tribe had which part of the value each times, and had this whole system again of credit, which is like pretty interesting. And then, yeah, you hear of things like people using animal pelts when there like wasn't paper currency or these types of things, or like people in jails using cigarettes as value. So again, it's like you have some like scarce object and you can use it to represent this valuable thing, this thing that we all care about, which is basically like, have I done something and do I think I get a reward? I just wanted to call out this book, Debt. I believe it's the first 5,000 years. David Graeber. Very good book. Goes into a lot more of this as sort of like an anthropological basis. And yeah, that's huge, very high level overview of that. Right. So we've had money as like, humans for millennia, right? And so now what we want is we want to put it on the internet because everything's moving online. We do all of our shopping online now. With the pandemic, we're all basically living online for better or worse. This class isn't in person or now on Zoom. But the thing that's tricky is that part of what's been so useful about these digital technologies is that the costs of copying some digital thing, like let's say a song as an MP3 or like a photo as a JPEG, like you can copy these for basically zero, no cost. So what that means is that if I were to just make, similar to how I'd have a digital representation of a photo as a JPEG, I could try and have a digital dollar as like, just a blob of data. But the problem then is that I could turn around and copy your blobs, and that just we can't build anything. We can't implement a thing that gives us the properties of what we want to call money if that's the case. So we kind of have had a problem. And then the problem sort of allegedly now is solved by blockchains. And this is Bitcoin, of course, is like the first example we have of this. So blockchains let us implement, something in the digital realm that acts like money, or at least we can make it act like money. And so now, they host cryptocurrencies, which again are these like representations of value, or at least let us, have these representations of value in ways that we couldn't before. So very high level. Okay, this is like a cute little thing I have. A way to think about making blockchains is like it's proofs and promises. So like really refers to cryptography. We have like, again, essentially like very advanced mathematics that say, okay, to incredibly high probabilities, this thing won't happen without some very specific conditions, right? So like you essentially have to like present a proof that like something happened. And this lets us replicate, say, property rights or ownership, because what it, the way this breaks down is I have some ETH on the Ethereum blockchain, and it's protected by a private key with a cryptographic public key. And then if I want to send some ETH to you, I have to produce a cryptographic signature. So you can think in some sense the cryptography is like protecting my digital asset. And then there's a lot we want to do that we can't with cryptography because effectively it's too expensive. But just people try to implement these things, and basically the running times of even the things we can write programs for just like are non-workable. There's a session later on zero knowledge proofs, and that one's really interesting and gets into a lot of this. But either way, there's things that today we can't prove. We're working on it, and it may be better in the future, but today too expensive. So then we try to close over those bits, and sort of when we're designing these systems with incentives, this is where game theory comes in. So this is why I call it proofs and promises. And essentially it's like, here's, if I can't sort of, guide your behavior with cryptography in this digital realm, I then have to like use some other incentive, say an economic incentive, to get you to act a certain way. And this was basically the breakthrough in Bitcoin. It was, we've had like cryptographic sort of ownership actually like decades before this. There's literature like Wei Dai has his B money, and again, there's a whole history here, not the subject of this talk, but the really cool or sort of key bit about Bitcoin here was that it said, hey, we're actually going to reward the maintainers of the system in the coin itself, and that actually aligns incentives in this like really interesting way that lets you build these these systems in a way that they aren't controlled by a third party. And the claim then is kind of that you need this aspect of neutrality for something to be money like. And I'm not going to like dovetail into all the philosophy here because we could get into it, but either way, that's what I'll say about that. Okay, but then now we're gonna get a little more concrete now and say, okay, what are these things actually doing? So hopefully you have some sense now of like, what a blockchain is and why we might care about it. We can again look to our first example, which is Bitcoin. Bitcoin is effectively a shared ledger. You get this one application that says we have these coins. You've seen this like BTC unit. Basically, the Bitcoin blockchain is this ledger, and it basically says, okay, there's a cryptographic address, and this address owns this many coins, and there's another address, and it owns this many coins. And from there, we can say, okay, I can produce a transaction. And what the transaction can say is, let's move this many coins from Alice to Bob. So like Alice, for example, could say, hey, send 10 of my Bitcoin here to Bob. Bob could turn around and say, okay, I'm going to send 4.5 of those Bitcoin to Charlie. And in this way, you can see how now there's like something that looks like money. You could imagine, again, just like a digital coin or like a piece of gold or something. And you're using this to like, transact an economic value. And again, there's a bunch of like incentives and like very interesting game theory that actually lets us, have faith essentially that the system will be around tomorrow, in as much as, certain actors in the system or in the network are motivated to maintain this ledger. So this was like, again, very groundbreaking at the time. And it turned out that it got a lot of people thinking about, oh, like, okay, we could actually have these like sort of digital native monies. What more can we do with them? And again, there's a whole bunch of history here. If you want to, most of it's probably on like the Bitcoin Talk forums, which I'm not sure if those are, I'm not sure actually how active they are anymore, but 5-6 years ago, a lot of the stuff happening there, and basically people had these schemes where it was like, okay, Bitcoin, like I said, Bitcoin, Bitcoin is this, we have one application, which is basically we have a coin as an abstraction and we can move coins around. But what if we want to do something besides move coins around? What if we want to attach additional information to these coins? Not so much just who owns them, but also maybe, who owns them, and we'll pick a property. This is where it gets tricky, because you could actually have any property. So I even give an example here. You could say attach not just some value to this coin, but also like a name registry. So in the same way like DNS works, you could say, okay, this account owns this coin, and coin now gets a little abstract, but essentially it owns this coin. It could also say that this account owns this string. The string could be like google.com or vitalik.eth. So it could be these strings, and where we're going with this is having a system on the Ethereum blockchain like DNS, which resolves, for those of you that don't know, resolving like domain names on the internet to the underlying IP addresses. And so at the time it was like, okay, we have Bitcoin, which is this sort of one-trick pony. It'd be cool to like have another application like this like game service. And so how are we going to do that? And then there are all these schemes around like there are these schemes called colored coins, where basically you could try to attach data in like very sort of clunky ways to particular Bitcoins. And then like you could see there's like a meta layer on top of the Bitcoin protocol itself that then has this information, and you could try and build clients and do all this. Basically, there was a number of like efforts in this direction. Like there was a name coin that did exactly this. And yeah, there was, I believe Mastercoin was like the colored coins project. Either way, people were trying to do this stuff, and they were trying to like build these applications on top of Bitcoin. But as we'll get to in a second, like part of the reason that Bitcoin is this way is because it's not trying to be, this sort of Swiss Army knife. And that was actually the original motivation for Ethereum was, okay, we don't need to have, one blockchain per application. We should just have one blockchain that can handle all these applications. And so where we're getting to is like kind of mechanically how that is carried out and how that happens. Yeah, so I have this little bullet point here. Importantly, like everything can talk to each other. So that's actually, I think, a point that's really driving the growth of a lot of this stuff. You hear like composability over and over again as being a strength of applications in this ecosystem on top of Ethereum. Again, there's a lecture later I saw in the syllabus on DeFi, decentralized finance, that we are going to look a little bit at today. I'm sure you'll go into much more depth in that talk, but either way, part of how we get that is because all of these different applications can talk to each other and talk to each other like really, really cheaply and quickly. Whereas like, even today we've had, let's say at least 10 years of like blockchain development in terms of like software development. And like, we barely have like very weak bridges between say the Bitcoin blockchain and the Ethereum blockchain. And then from there, there's like bridges to other chains are like either non-existent or very, very underdeveloped. So anyways, the point being that it's actually really, really helpful. And, we get a lot of utility of the fact that we can co-locate all these applications. Which brings us to the topic, which is dApps. So dApps, again, decentralized application, kind of like what I said, rather than having to like build your own blockchain, one blockchain per application, we can now reuse a lot of this like shared infrastructure. So if you look into this stuff, the blockchain clients are open source. You can go find the Bitcoin Core client. You can go find, the Go Ethereum, the Geth client. And all of these things, there's huge code bases. Like there's been like tons of work that go into them. There's like very, like almost black magic networking layer. On top of that, you then have like this sort of core consensus. So then the client has to like get all these messages from the network and figure out like what everyone else thinks, right? And then you have consensus. And then on top of that, there's like some notion of network security. And basically all of this is either like a huge complexity burden in terms of like development maintenance, or it's like actually expensive. So an example of security, you basically have to spend, you have a security budget. So it's like X amount of dollars are securing, the activity on your network. And what that means is that if you can reuse this stuff, you definitely should, wherever you make it. And so that's what we're seeing on Ethereum, is that we can say, okay, let's share the networking layer. Let's share, sort of this data layer of the actual chain itself. And then we have all these applications that sort of sit on top. And moreover, because they do all share this sort of common substrate, they can all talk to each other. And that actually just like amplifies the space of possibilities. And so now, like say, the barrier to entry is much lower in terms of actual blockchain development and sort of in terms of building these applications in this new way. And we're like off to the races. I'm gonna grab a little water, but I have this next slide here, which is an example of, let's see, what would this be? This is essentially like contract interactions. So the way to think about this is like different apps. It's like visualizing the ways that different apps can interact with each other. Here are some dApps. Here are like some of these applications on Ethereum, like MakerDAO, like Uniswap, like Compound, like Augur, and we can go into maybe at the end, like in more detail about these if you'd like, but either way, you have all these applications and you see it's like, okay, there's like so many people that have like taken loans on MakerDAO, and that's all these like, this is like, it's the biggest bubble here, but this constellation of all these little blue dots. But then what happens is people are then, they're drawing assets against collateral in these loans, right? And so now you have the stable coin DAI, and that's what this like little, oh wait, you can see my cursor. Okay, so this little constellation of these dots here is like people who are taking DAI from their MakerDAO positions and then putting it into Compound, either to like borrow or supply. I suppose they're supplying it, but either way, they put it into this Compound market. And then we see here, there's all these network connections and things. The reason I put this here was to show you with the next slide. So this is November 2018. At this point in time, it was like DeFi was like on the horizon. It was like something we were talking about, but it really hadn't quite been proven out, at least in the way that it has now. Because now you can see a similar graph from earlier this spring. This is just like absolutely exploded. And this is, I mean, I can tell you, this is a tiny fraction of like the space of DeFi that's happening on Ethereum today. And this isn't even looking at like other blockchains, other decentralized applications, all this stuff. It's just absolutely exploded. And at least in Ethereum's case, a lot of this is because of the way it's designed. You can have these contracts, these dApps that can talk to each other, again, really easily. So then you get this composability almost for free. And now you can say, okay, there's a community that's like focused on making a platform to trade these tokens. And then now you have other communities that are like letting you like use the tokens as collateral. So now you can like draw a loan, and then the loan can be used to like, you know, get leverage as like trading and synthetics, which is another exchange. And anyway, you'll get into more of the details of DeFi itself, but the whole rabbit hole into its own. Very exciting. So I forgot to put this in, but basically the point I was trying to make here is that you might have seen early images where it's like the early ARPANET connecting just like a few universities in like, you know, what, the early 70s or something. And of course now the internet is just like this absurd thing. There's just a bunch of tubes. And anyway, you'll see stuff in media about this stuff trying to make similar connections that like DeFi is going to blow up and do a similar thing. Who knows about all this stuff? Just a disclaimer, right? This is all super early experimental technology, but either way, it's a lot of fun, and we'll see where it goes. Okay, so another analogy to the web today, and this is for dApps in particular, is like I want to get across this notion rather than thinking of them as like decentralized applications, because I find that kind of like trips people up. One way to think about them is like sub protocols. So you have like you have Ethereum, right, as like this blockchain protocol. Then you have sub protocols, right, protocols within the Ethereum protocol, and these are the dApps. And again, an analogy. So we have Twitter, Facebook. You know, pick your web app today, but they're sub protocols of like HTTP, right? And then HTTP in turn is like running on top of TCP and IP protocols, and it's just this layered thing that provides all these, you know, different layers of the stack, and then end up being able to specialize into say like the Twitter protocol, like, you know, like Gmail is almost its own, you know, protocol itself that's replicating email. And either way, that hopefully is like a mental model that will help. This is a bit of an aside, again, because I do have blockchain scalability on the mind, and it is super early. So some of this maybe is like TBD. We may not need it. It may be super important. Who knows? But essentially, we're likely to have layers of the blockchain stack in the same way that we have layers of the internet stack, right? So, and again, this is an analogy to TCP/IP. I wonder. There we go. Yeah, TCP/IP. And like applications on top of that, right? So like, you know, at the bottom, there's like Ethernet, then like, you know, IP packets end up inside Ethernet frame, TCP on top of that, HTTP on top of that. So now there's layers to blockchains. And so Bitcoin and Ethereum, these are, you'll hear the terms like L1 and L2, like layer 1 and layer 2 thrown around. You can imagine like a layer 3, but again, we're still working on building out layer 2, so it's and it's not even clear that layer 1 is going to get us what we want, so that might be getting ahead of ourselves. But either way, if you get into stuff, you'll hear layer 1, 2. Some layer 2s you might hear about are like rollups, like optimistic rollups or ZK rollups. Plasma is another one. State channels. There's a whole zoo here of like, you know, points of design space, and again, we could chat about that a bit towards the end. But I just wanted to mention it just so you have to it, I guess. You'll run into it.
So just places. A quick question, Alex. So your layer 3, is it more like going to be like a cross-chain type of?
Yeah. So again, layer 3 is, I don't know if anyone even really talks about layer 3, but the idea would be, right, so there's like, let's say Ethereum is our layer 1. Then we could have like an optimistic rollup that sits on top of Ethereum as the layer 2. What that means is that you could basically imagine there is another blockchain that essentially every so often the state of that blockchain is committed to on L1, on the base layer. And then what that means is that all the transactions at L2 don't have to end up on the base chain at L1. And so that's how you get your scalability. And then from there, you could imagine now we have multiple L2s, and then so the big thing here is like, we want to actually be able to have the same notion of composability I've been like harping on between applications. And if the way we scale is we put an application to a layer 2 construction, then there's not a direct way for 2 different L2 constructions to talk to each other. So then we may want ways to like have them talk to each other. And then, yeah, it's, you know, cross shard, cross chain. These are all kind of getting at the same notion of, we have these like distinct systems and there's not a direct way for them to communicate. So like, how do we do that? So yeah, but you're right. Like as an example, like we could imagine some layer 3 thing where it's doing some like weird optimistic locking between parts of like DEX state on one L2 and to another L2. Yeah, so at this point, this is just like super experimental. I'm just kind of riffing, but there's a lot here. I mean, the point to take away from this just now is like there's a wide open design space. We don't know how this stuff is going to work because it's so early. So like if you're interested in this stuff and you're listening, like very much please, you know, get involved. Okay, and just to round this out, here's, and you can see I actually had to like cram the slide in a bit, and of course there's more stuff in this, but some examples of dApps. So the common example would be like just tokens, in the same way that like BTC is a token on the Bitcoin blockchain. Now you could have, you know, pick some token. Like maybe you want a different issuance schedule than the BTC token provides, or you want a, you know, different, like maybe you have something where for every transfer of this token, it actually like sends part of the, you know, transaction value as a fee to like a common treasury. Like there's all sorts of things you could do. If you want to have your own semantics around, you know, these token transfers, then it turns out we have a standard for what a token should look like, an ERC20. And this is just like, you know, if you have an interface and, you know, pick your programming language, right? It's the same idea where it's, you have like some behavior and you have different implementations of the behavior, and maybe they're like a little bit different, but in the ways in that you care that they're similar, right? They all conform to the interface. And so ERC20, you'll hear this term thrown around all the time because people just love tokens. And ERC20 is our token interface on Ethereum. So that's an example. Another example would be like even just a loan. And again, this touches on some of the DeFi stuff, but MakerDAO is like probably the premier and or the earliest example of this. You could think of it as a decentralized credit facility. What that means is that basically I could lock up, say, my Ether as collateral in the system, and then draw debt against this, right? This collateral I've locked. And it turns out that the unit I can draw against my collateral is called DAI. And there's some like very fascinating economics and like game theory involved to ensure that the value of one DAI is like targeting $1. And then that leads us to the next category, which is stable coins. So again, it's like if you follow this stuff at all, you'll see that, you know, Bitcoin and Ethereum, or Ether, I should say, they very much have a price, but it's all over the place. It's like super volatile because this stuff's early and there's a lot of, you know, speculative activity and all this thing. So it's really handy is to have the properties of these programmable currencies, but, you know, you might not want to be exposed to the price volatility of these assets. So then people have made these derivative constructions, examples being DAI from MakerDAO, or even like USDC. And, you know, there's, again, a whole industry of stablecoins popping up. But either way, the whole point there is that they target, say, $1, or, you know, there's some fixed peg that they target to not expose the end user of the holder of the currency to the price volatility. Another example would be a decentralized exchange. You'll hear DEX again. They've gotten really popular, especially this year. Again, Uniswap being the premier example. This is very much like, again, like if you go to a stock exchange, right? Like if you have a brokerage account somewhere, you could like go and like buy shares of, let's say, Apple, right? So then you like trade your dollars for shares in Apple. Similarly, you have like, say, DAI and, you know, MKR, which is the governance token to MakerDAO. And let's say you want to like trade those, right? So Uniswap facilitates that trading on chain, which is super cool that you can even do. Another one would be prediction markets. Examples are Augur, Omen, games, NFTs, that's short for non-fungible token. So whereas an ERC20 is fungible in the sense that, also fungibility in general is like if I give you $1, you don't really, like let's say I have like $4 bills and I'm going to give you $1, you don't care which dollar I give you, right? Because they're fungible, meaning they all like $1 is $1. If something is non-fungible, then it actually does matter. So an example could be like tokens that map to like, well, I guess we'll use a crypto example. I mean, like a big one is like, you could have a token that basically maps to a work of art, right? So let's say like the Mona Lisa was tokenized on the blockchain. Then you would basically have, you know, the smart contract, which again, we're about to look at, and that'll make sense what that means, but there'll be, you know, on the blockchain, there'll be a record of, you know, these tokens that map to this work of art. And then you could imagine fractionalizing the work of art, because now instead of just one token, maybe there's 100, right? So now it's kind of like owning like, you know, one token is 1 out of 100 shares in this work of art. Anyway, again, there's like more here than I'm gonna like have time to talk about in like the next hour or whatever, but big stuff. You're in the right place. Oh, okay, DAOs. Well, so this one's actually really interesting. A DAO is a decentralized autonomous organization. And the idea is that we essentially want to organize people and or capital on chain. What this means is, you know, a very common mode of organizing people today in society is like a for-profit company, right? So like a Delaware C Corp, you could say, right? And then you have a firm and people come to the firm and they produce work, and, you know, this is how we organize and structure society. You could basically start to like represent these different functions in code, and then now you have this thing living on chain that is now like taking contributions of labor or capital. And again, I'm not gonna have time to do it justice, but there's like a whole design space here for like sort of novel ways of like organizing really just people across the internet. Super fascinating stuff. Okay, so we're gonna now get into, you know, very specifically like Solidity and EVM and smart contracts themselves, and look at some code. I just wanted to stop for a second and just like ask generally if there are any questions so far.
Well, very fascinating, very exciting.
It's okay if there aren't, but I also, yeah, I don't want to be boring anyone, and I can't see anyone's
And by the way,
reactions.
this is we've never
Wait,
had
can
this
you
many
explain the
participants.
quadratic voting?
Sure, I just glossed over that. So let's see. So this is an example of what I mean when I say that we have a chance to experiment with like different ways of organizing, you know, people in the world. And here's an example, and it'll make sense what I mean by that. So that, because that's a pretty abstract statement, but what I mean by like, yeah, so the example here is quadratic voting. Traditionally, if you think of like, say, a democracy or like, you know, anything where we're voting, you know, we could say, okay, well, here, how about we like have this example here? So we're all in this class together. We could say, let's vote on what the next lecture should be about, right? And we have options. Everyone gets some tokens, and basically you could say one token corresponds to one vote. And then we could even go further and say, oh, there's now a smart contract on the blockchain that what you could then say is, okay, you could think of it as like depositing your token in one place or another, and in doing so, you're signaling that you're voting for one lecture over the next, right? So already here's like a cool example of like something you can imagine. Quadratic voting in particular is actually saying, okay, are there better ways to vote? With the example I just described, we basically, and this is actually a lot of the stuff works today, basically say one token on the blockchain. So people do actually do this type of voting where it's like, you know, so an example that I could give is MakerDAO that I just mentioned, where it's this whole like, you know, some people almost call it a decentralized bank, because basically it's very much like a central bank where they essentially have to like manage, you know, there's like a debt ceiling, and their whole, because they're, you know, again, their whole mandate, which again, if you follow this stuff with the Fed and the central bank, it's like, it almost snaps 1-to-1. But basically, there's a mandate of the MakerDAO DAO, people who are part of the MakerDAO, And what they effectively have to do is manage risk of the system such that they maintain the price peg of one DAI as $1. So, sorry, I'm realizing I'm just throwing a bunch of stuff at you. And if this stuff isn't clear, it's going to be easy to get lost. But either way,
the thing for me is I just don't understand how it's quadratic and that kind of.
Oh, we're not there yet. Yeah.
Why would you use that term?
Yeah, we're not there yet. Sorry. So we're voting, and then it turns out that if we're voting, basically then it turns into what we're going to call a plutocracy, which is essentially $1 is one vote, which doesn't, mesh very well with a lot of people's understanding of how we should be able to express, our desires or our preferences, right? So one way to think about mitigating this is a mechanism called quadratic voting, where you say, okay, rather than it be one token, one vote, basically the votes you get scales quadratically. Well, I should say it takes a quadratic number of tokens to express, that much voting expression power, so to speak. So for example, rather than 10 tokens means I have 10 votes. Well, let's use this square. So rather than saying 16 tokens is 16 votes, 16 tokens is only 4 votes. And so basically it's scale how much influence you have, via how much capital you have lying around. And again, this is to close the loop. This is to try to mitigate this issue where you could have people who maybe have a bunch of these tokens and maybe they're not super active or like super interested in a particular issue, but they could still, come in and like swing the vote at the last minute. So yeah, that's what I mean here by quadratic, is just that there's like this nonlinear relation between sort of your voting power and like the signal of the vote. And the point here being that, zooming out, because I know we got way down in the weeds, but zooming out a bit, the point here is that in this example in particular, at least, what it means is that we can experiment now with these things that before, for either like legal or regulatory or just like, means of inertia, we were not going to be able to really probably ever do, right? So like, for example, like we'll almost never see quadratic voting, like at least I don't think we'll ever see quadratic voting implemented in, say, like an American election anytime soon. It could be the case that this is like super successful at like mitigating some issue that everyone sees or agrees happens in elections, and then maybe it bubbles back out. And that's a lot of what I see is really exciting about DAOs in particular, is this opportunity to experiment with these ways of organization that we just, really practically wouldn't be able to otherwise. Did that answer your question? I know I kind of walked all over the place. Okay, cool. You're like, that was way too much. That guy needs to stop talking. Okay, so we're gonna dig into smart contracts. And okay, so yeah, hopefully now it's like you at least are vaguely interested in like why we care about these smart contracts, the dApps, and all these things, like why it'd be cool to have a programmable blockchain compared to, say, Bitcoin that is not programmable. And the way that we do this is we're going to have some notion of Turing completeness in our blockchain itself. So as it turns out, the way that you make one of these things, this blockchain, we weren't very clever when we named it. We really just mean a chain of blocks. You have a block. The block has, one thing it has is a reference to its parent via its hash, the block hash. It also has like a bunch of transactions, and these transactions have a particular order. And so the idea is that if we start from the genesis state, from the very first, we all agree to some starting state. If we start from that state and we play all transactions in the exact same order, then it turns out that because these computations are deterministic, we end up with the same state at the end, right? And this is like, this is the bread and butter of how these blockchains work. This is why we like talk so much about consensus, is we need to have, there has to be a global ordering of transactions on the network, right? So anything that we see, this could be like 10 years from now, halfway around the world, you need some way to figure out the order of transactions I view today. You need to have the exact same order, because then then we can agree and we can actually have like actual shared space, shared ledger. To give you like sort of an everyday example, it's like just look at your bank account statement. This is what they do. It's just a list of transactions you make. You start with your beginning balance. You sum all the debits and take away all the credits, and you have an ending balance. And this is the same thing. Let's see. Okay, and so then, like I'm kind of getting at with Bitcoin. So in particular, the Bitcoin computer, there's a virtual machine embedded into the Bitcoin client. I'm assuming most of you know what a virtual machine is. Essentially, the idea is we like emulate a computer. So there's like these low-level instructions that say, hey, take this number and add to this number, take this number and subtract this number and do all this stuff. And that's how you sort of express the effects that you want in your virtual machine. So either way, Bitcoin has one of these. It's called Script. It's actually like relatively simple, again, because it's kind of by design, limited to not be that complex. It's a stack-based language. If you studied virtual machines, that means something to you. It just refers to like memory organization, basically. And again, the only thing you can really say with Script is, verify the cryptographic proof that you own these coins. And then if so, you can basically move them to another address, right? And then the way that Bitcoin actually works is transactions are just like these, again, they're chains of these commands of, here are some coins, move them to like the next address. Here's some coins, move them to the next address. And you just do this, forever and ever. There is support for multi-signatures built into Script. And so what that is rather than just requiring me to say, yes, I own these coins, now move them over here, you require multiple parties to sign off. And there's a number of reasons you might want this. So like, it could be handy if you like, let's say you want to have like a trust of Bitcoins on chain and you have like multiple parties that are like governing these coins, right? You might want to say have 3 out of 7 of your board members like sign off on something before you like move some funds. And you can do some very basic computation, but like, for example, a big thing you can't do is like write a general for loop. You can't say, okay, for every address in this transaction, do some computation. And again, this was by design. I think this, yeah. Well, so here's an example we'll get to in a second, but it was by design because the claim was essentially the more general thing that Ethereum does is actually like less secure, or at least it's harder to get right. And so the thinking with Bitcoin was, let's do one thing very well, and that's what we're going to do. There's actually sort of like greater space for attacks to be carried out if we have this like more general Turing complete VM. And here's like an example of Script. You can look at it from different ways, but basically, there's like the raw sort of encoding of the bytes. The bytes are, the byte codes of the VM, which, by the way, if that's unfamiliar terminology, like speak up or signal somehow and I can explain more. Otherwise, I'll just assume you know what I'm talking about. But basically, there's these like core instructions that tell the Bitcoin computer like what to do next. And an example here is this is like a very standard Bitcoin transaction, which basically just says verify that. So the way it works is you basically have your public key that is put on chain or in the transaction, verifies that the public key hashes to this pub key hash, which is actually how Bitcoin addresses are. You then verify that it's equal, and then you actually check the signature. And we can work through this step by step if you want. It's not super relevant other than the fact that it basically just does what I said, which it checks that the addresses match, and then also that there's a valid signature. And so what that means is person who did own these coins, in fact, signed off on the fact that they want them to be spent. And it's kind of it. And that already you can see that we can't quite say that much. This page here, the Bitcoin wiki for Script, it goes into a lot more detail. That's where this example came from. And I'll point you there if you want to see more. Oh, I just exited this. Sorry. Nope. Oh, maybe that doesn't matter. You can still see the slides, right? Yeah, we can see.
Yes.
Yeah.
Okay. Yeah, I just exited the full screen. I wasn't sure if I messed something up. So, like I said, Bitcoin is simple on purpose. Again, the rationale is kind of it's easier to secure something that's less complex. There's like less attack service, all of these things. You don't want to like pay for the complexity budget, right? If you can get around it. And that being said, like I alluded to in the beginning, there are all these thoughts and ideas around these like more advanced applications that did more than just like a simple token transfer. And so that's where, you know, the idea for Ethereum was born. Again,
I had one question. So these, you said before something about having multiple people sign off and then having the Bitcoins being paid out. What actually does a sign off look like in Bitcoin script? Like how would somebody sign off?
Right. So if I'm lucky, you can still see my screen, right? Can you see that going to the wiki page here?
Yeah, I can see.
Okay, cool. I think it's in here, multi-sig. Oh, maybe not. Anyway, so I believe the way that this works is it goes one by one. Oh, here, let me just, oh, this isn't what I thought it was. So I believe the way it works is that how it would look is that, so the way that Bitcoin transactions are generally structured, which is actually a little bit different from Ethereum, but the way that it would generally work is that, let's say we want to do 2 of 3 multi-sig, meaning you want, rather than just one signature to move Bitcoins, you now need 2 out of any 3, or any 2 out of 3 possible signatures to actually move the coins. So then what it would look like is the coins would be moved into an address. I'll use the word encumbrance, but basically like the way that you then can move the coins is you have to have a 2 of 3 proof. And the naive way to do this is you say, okay, the way it looks sort of, are you familiar with what a UTXO is?
No, sorry, I'm new to
No, it's
crypto.
fine. No, it's all good. I just want to calibrate before I go off in a rabbit hole. So the way it would look is that essentially there is, let's say a reference. I mean, people talk about it being a puzzle. Basically, how it would look is that you could go on chain at any point in time and you would see that this multi-sig has been set up. And like the things you could take away from just seeing that public data like on the chain at that point in time would be there are 3 addresses and some other script that says this is a multi-sig. And then the way that you would spin the coins, to answer your question, is you would then later have another transaction that says, hey, I want to spin these coins. Here's 2 of these addresses. And then the way that I believe it works is that, and this is what I was trying to look up here on the script wiki, but either way, I believe the way it works is it actually just goes one by one and says, okay, for the first address, check the signature against each one of the pair. If that doesn't fail, okay, go to the next one in the set, look and check the signatures that were provided. If that fails, go to the next one. And then eventually you'll do this like pairwise thing until you find 2 that match if the transaction will succeed, and then you can move ahead. Does that make sense?
Yeah, I think I have a general idea.
Okay, so I think you could imagine like a more like sophisticated multi-sig operation, but then you'd basically have to, I mean, the way Bitcoin would work is you'd essentially have to bake that into like the client itself. Whereas like in Ethereum, you could like, you have the ability to just like express that more directly without having to change the underlying protocol. And one reason you might care about this is it's actually very hard to change the Bitcoin protocol. Some would go so far as to say that you can't really do it anymore. There's this whole notion of like protocol ossification, which again, we're not going to go into right now. Basically, it turns out that you may not want to change Bitcoin, and you could claim that that's good for its security, right? If it doesn't change. And so because of that, then there are many people with many vested interests making sure that you can't change the protocol, which is fine. If Bitcoin does, like if Bitcoin works for you, then that's fine, right? There are a lot of other applications besides Bitcoin that we could imagine. And this is kind of where Ethereum again stepped in, was saying, hey, what about all this other stuff? We should actually just make a sort of base protocol that can do the generic thing and do it well. And then people can safely build all these applications on top. Was that helpful?
Yeah. Oh yeah, definitely. Definitely. Thank you.
Of course. Yeah. Any other questions?
So, sorry, I'm kind of new to this as well. So my understanding is that Bitcoin didn't originally have these, essentially these, I guess let's call them smart contracts, these scripts. How how does that get added into Bitcoin afterwards? Like, how does that process work? Because it seems weird to me that you could do that to a ledger that's supposed to be you can't change.
Right. So like basically, how would you extend the Bitcoin protocol with new stuff? That's the question.
Yes, specifically, I'm interested in this particular case of these scripts.
Sure, yeah. So, okay, first thing, don't worry if you're new, because literally everyone is new. Find the experts in the space, and they've been studying this stuff for like at most 10, maybe 15 years, if you want to even go before like stuff we'd actually call crypto. So like everyone is new. We're like all learning together. So don't let that stop you from like asking a question or like trying to figure out what's going on. Unfortunately, this stuff is also all very complicated. So there are definitely like many questions to ask aside. Okay, so if I'm hearing you correctly, the first thing is that, so this actually is the way that Bitcoin works, is that everything is like a statement in the script, this language. So even just like the, I mean, this is what I was trying to get at with this example, is that even something as simple as just moving one Bitcoin from me to you, you write it in script. And so every operation on the Bitcoin blockchain is done via script. That being said, again, there's a very narrow set of opcodes or sort of semantics, operations, things you can do with script, and that actually limits the expressiveness. If we wanted to extend it, we would have to essentially, in Bitcoin's case, coordinate what's called a hard fork. What this means is that there are a set of rules in the Bitcoin client, right? So I mean, if you think about it, like the Bitcoin client, its only purpose is to like operationalize this fact that we've all agreed to a certain set of rules, right? Like you can almost ignore the software. There's a shared contract that like we all believe in this value thing, and then the fact that this value can be transferred, and like, you know, there's these semantics attached to it. Like this is the thing we've all agreed to do. After the fact, we've decided to write it and sort of encode it in software, and that's the artifact. But the high level thing is that there's just these abstract set of rules, right? So the way it works is because consensus is so critical. If you want different rules, at least rules that are inconsistent with previous rules, you have to basically write a new client that is incompatible with the existing network. And the reason it's a fork is because you can think again of this chain of blocks. See, I don't have a nice setup. Like if this were like at a whiteboard, I could actually draw this out. And I think some people do this with tablets and things, but anyway, there's a chain of blocks, and then you could just literally imagine we have shared rules up until like this block at this height, and then you could add a block here with the old rule set, but you could also add another block over here with the new rule set, and then basically build a fork off of here. And that's what happens. I mean, there have been many forks in Bitcoin's history. Yeah, and like again, this is like a whole different talk, but basically, you know, one example would be Bitcoin forking into Bitcoin Cash. Right, this is, I believe, in 2017, yeah, where essentially there is a huge debate over the block size. So I mentioned, right, that blockchains are these linked together bits of blocks. The blocks are, you know, you can serialize the blocks as these bytes, right? And so then the question is like, okay, how many bytes, how big should the blocks be? And the reason this is important is because if you have bigger blocks, you can fit in more transactions. And if you can fit in more transactions per over unit time, right, then you could theoretically scale the blockchain because, again, more transactions per second. To give you a point of reference, like Bitcoin today is maybe around 10 transactions per second. Bitcoin, Ethereum, roughly order of magnitude, 10 transactions per second. Something like the Visa payment network is processing like 10,000 transactions per second. I think they can peak up to like hundreds of thousands of transactions per second, right? So orders of magnitude difference. And if we expect to build, competitive payment networks at these base layers, then we're gonna like need to do something, and probably something drastic, right? Just because the differential is just so great. But one thing we can imagine doing is making really big blocks. So right now, a Bitcoin block is capped at 1 megabyte. Essentially, I think technically it could be like 3 megabytes now, but it's counted as 1 megabyte. And again, that's a whole different conversation. But the point being is there is a huge debate. Everyone was on Twitter arguing about this for like months, because the reason we care is because the bigger the blocks are, the harder they are to process. And so again, we have very strong norms in this community around like crypto in general that we want, we don't want to exclude certain people from like participating in the network, right, if they choose to. And this gets into this like notion of decentralization, where the more people you have contributing to the network, the actual more resilient it is, right? Because you don't have these like singular points of failure. To give you an example, you could imagine like, there's some legal action against Visa and they're taken down, and then suddenly like this whole payments network that, we may use, right, to like, or better examples like Venmo, like I could send you money on Venmo, but then like, let's say for some reason there's like legal action against Venmo and they're taken down, and suddenly like, I can't do this, right? It'd be very nice if we have institutions like this that could like last as long as we want and aren't really subject to these sorts of pressures. And the way that we achieve this is via decentralization and having these like really strong, diverse networks. So it's very important to close the loop. It's very important to have, blocks of a certain size. You don't want huge blocks, because that means that only specialized actors who can like either afford or have the ability to put lots of capital into specialized hardware for processing these bigger blocks, can do this. So, sorry, you asked about forks. So basically, yeah, there is this whole thing about block size. You have to change the protocol, and like in Bitcoin's case, it's very hard to do. For Ethereum, I would say maybe we're a little more friendly to forks, but that's more just because it's like, hey, there's like very specific things we need to do to like change how the protocol works, and it's usually pretty clear that they're like net wins for everyone, and so then we can like pull them off. But then even still, it's like we at this point probably get like one hard fork a year, and like there's just like so much work that goes on behind the scenes of like actually pulling that off, just because like it may sound simple, but it's actually really complicated, because in part because it's like you can't just like go to one central actor and be like, hey, update your software. You just have people all over the world running this stuff, and like you have to hope that they hear about it and agree and can actually deploy these changes.
And also, if I were to just add one side comment, is that in Bitcoin, nothing has changed. So the original language is, we can say, more or less is the exact same thing. So now if you want to be able to support more interesting application, as Alex was describing, you got to go to layer 2, because in layer 2, you have a lot more, so you can pretty much do anything you want in layer 2. But in Ethereum, from the start, they had the smart contract. So they had this Turing complete language. They weren't limited to this unspent transaction model. So the limitation of the Bitcoin doesn't really exist in Ethereum by design from day one, pretty much.
Exactly, yeah. So we wanted, there are other parts of the protocol you could like imagine you want to change, but this was apparently an important one, was to have the ability for the sort of end user or the developer to be able to specialize the blockchain software in this way. And so here we are. So, okay. I'm happy to field more questions. We're maybe we should keep moving, I suppose. There'll be time at the end for more questions. But now we're going to look at the EVM, which is, in the way that we were just kind of discussing the Bitcoin computer, we could talk about the Ethereum computer. And whereas like there is a Bitcoin VM script, but it's kind of like, it's not necessarily a very direct thing. That was, again, kind of the bread and butter of Ethereum, was to have this like Turing complete VM. So you see it a lot more, front and center. And this is the EVM, the Ethereum virtual machine. Okay, the EVM, again, at like a super high level, it's a stack-based VM, also like script, but then there's also like there's an ephemeral memory, meaning that during the transaction, there's like memory, like you'd have RAM on your computer. There's like memory sitting there for a sort of smart contract execution. Very helpful also is that there's persistence memory. So like you can imagine there's like your hard disk on your computer. We have that. Basically every contract has its own local storage or private storage. I hesitate to say private because, again, everything is public on chain, which I'm sure you guys have touched on that somewhere else. But the key bit is that it's not just that, you can have these like sort of, we could call them pure functions or like just pure computations where here's some inputs and mapped to some outputs. You can actually now have like stateful execution. And again, the whole point here being, without getting into too many specific details, is just that we can now have these like very rich applications on chain, and it lets us, implement these applications, right, that we may want that either weren't possible. I mean, yeah, they just weren't possible before. So the EVM has rich memory, is the point there. It has, again, these opcodes, these like sort of very small operations for things like basic arithmetic. So like adding, subtracting, division, multiplication, bit shifting if you need to do that. Logic, so like, like logical and, like a Boolean, control flow. So like if some value is true or false, go over here in terms of execution. And again, if you've studied, this stuff, you'll see this is very much just like, how we think about building computers today, like general purpose computers, right? So yeah, like here we are in EVM. We've done this on Ethereum, and it's great. If you have a transaction on Ethereum, essentially there's two types. So the first one is, you can almost imagine it's like hard coded into the computer, and it's like transferring ETH. Whereas like with Bitcoin, you're pretty much transferring BTC. We now have Ether transfers, and the way to think about it is that, again, they're kind of hard coded as a special case of like, okay, here's an account, and this account has some Ether, and then I could actually just move Ether. Separately, I can have a transaction that goes to a different account that has some stored bytecode, which we'll get to in a second. But essentially, it's stored. There's code that's already been deployed onto the blockchain, and I can interact with it by calling it as a transaction. So I can say, rather than send ETH from Alice to Bob, I can say send ETH from Alice to insert smart contract address. And we'll go look at that, and it'll make more sense in a second. But for now, just stay with me. And what happens in that case is that if there does happen to be bytecode there, the bytecode is loaded, and it's actually executed against your transaction input. So very much just like a computer would do. And this is how you get this like smart contract thing. If you have studied databases at all, there's this notion of like stored programs, which is like, I think, very analogous to my understanding, where basically like you actually like send some code into like your Postgres database. And so you could call it to execute against like inputs and store data and stuff. Very similar idea here, where you can deploy some bytecode onto the blockchain. It's stored forever. Anyone can then call it and hand it tokens, hand it Ether, like whatever they want to do, whatever, and then the contract, written into the EVM bytecode is like the functionality of the contract. So it could be like lock up my coins for 400 blocks. It could be trade my tokens for these tokens over here. I mean, again, like the sky is the limit, and we're just at the very beginning of trying to understand like what all is possible with this stuff. And when people say like call a contract, this is what we mean. It's sending a transaction to one of these deployed units of code. The code then executes with the transaction as input and does some stuff. Here, let me look 1 second. Well, okay, we'll just push ahead. So I was going to jump to, there's this handy website called EtherScan, where basically it like kind of is like a way to view the blockchain, and we could like see a little bit more concretely some of the things I'm saying. But just stick with me for like really one more slide, and then we'll get to something that's a little less dense, I think. Okay, so we now have this like super general like, you know, computation context on the blockchain. Like, that's awesome. Are there any problems? And like, you know, I kind of alluded to it earlier, where with Bitcoin, the issues are, you know, there is an explicit design choice against this because, you know, of security concerns. And to give you an example, let's say now we do have this like Turing complete blockchain where anyone all over the world can like deploy arbitrary code and then do arbitrary things with it. Something I could do is like, let's say you're humming along, like processing blocks, everyone's like sending transactions and trading tokens, and then, you know, everyone's having fun. And then suddenly like I broadcast a transaction that executes like an infinite loop, right? Because again, I told you like this is a generic computer. So one thing I could do is just say, you know, for, you know, forever, while this thing is true, and this thing could be set to true such that this always executes, right? Do some stuff. And what that would mean is that every node in the network would like get to that transaction. They would start to process the transaction and they would never leave the loop, right? So that obviously then is terrible because it basically just halts the whole network, right? So we can't do that. And the way that we get around that is we have to extend our computation model with not just like, here's this Turing complete, you know, environment. You now have, you know, we could think of it as like metered computation, where you basically have to pay for what you use, which makes sense. The units of this consumption are called gas. You'll hear that if you're in Ethereum at all. And the way it works is that basically every byte code that you execute has some gas cost. I'll skip ahead because I think this might help. So here's an example here of like some byte codes. You know, this is like, you know, so this is like a hex encoding of like what would be in the transaction. And here's the link if you want to look at this later. I'm not sure what this does or if it's like super, it might just be more an example, but either way, you know, it's like when the EVM goes to interpret, you know, value byte 34, it executes the call value opcode. And what that means here in particular is tell me for this transaction, was any ether sent, right? And that could be like no ether, it could be like, I mean, pick your value, right? So it's just telling me if there's ether attached. The next one is like, so this is like, again, this gets to like the low level nature of this environment. Dupe1 is saying basically duplicate the top stack item. And again, this gets down just like the very low level mechanics of the EVM itself. You know, generally in high level languages that you're used to, like say Python, like you're not thinking about this type of stuff. And that's because, you know, you're targeting a higher level. And Solidity, where we're getting to, is that higher level language that we have. But again, we're still at the lower level. The EVM, I should have said this. The way that you could think about this is like as assembly. So like if you are familiar with like assembly programming, say like x86, right, on like your laptop, the EVM is like the version of assembly that's executed on chain. And like it's super low level, like you really wouldn't be writing this manually, but it's ultimately what's executed at the bottom of it all. So either way, the reason I skipped ahead was because, again, I wanted to point out each opcode. And so each opcode here, right, has some gas value attached. And then what that means is like, you know, let's say it's 5, 10, 5, 5, 5, 10, 25, right? You basically, for every executed opcode, you sum up all the gas and you'll get like 25,000 gas. Then what happens beforehand is you commit to a gas price in the transaction. And we'll look at a transaction in a second to make that more concrete. But basically, you commit to a gas price. You multiply how much gas you used by the gas price, which could be like, you know, 10 to the minus 9 ether per gas would be like a somewhat reasonable gas price. And then that basically is an amount of ether that you have to pay to have your transaction included. And this is the transaction fee. Maybe I'll do this now. Just to give you a rough sense of like, there's actually a gas market, right? It's like people use this stuff actually. And so these are actually relatively low right now. Like over the summer, for example, like these were up. So, okay, there's a gigawatt, which is a unit of ether. The way that a dollar is divided into cents, a Bitcoin is divided into Satoshi, and an Ether is divided into Wei. Just for the reasons that we have, one Wei is 10 to the minus 18 Ether, right? Or like 10 to the 18 Wei is one ETH. So this gigawei would be 10 to the 9 Wei. So basically, it's a very, very small amount of Ether, right? So let's say if I have 500,000 gas, well, we'll just tell you, right? So 500,000 gas, and let's say we do 40 gigawei per gas. So that many gigawei, and then divide by 10 to the 9th. Is this gonna work? Okay, I should not have done that live. Anyway, we can circle back to that. But the point being is that there's a fee. And yeah, gas is what I was talking about. Is the gas, here's a gas schedule. So again, it's like, here are these opcodes, right, that we saw. And ultimately they end up costing some gas. So like if I were to execute the add opcode, which is like adding two integers together inside the EVM, I'm gonna pay 3 gas. So hopefully that makes sense. That might have been a lot. And one second, someone was asking for this link.
I will have the slides shared with everyone, so I think they can.
Okay, yeah. The slides should come out. Yeah, they'll be around. I just lost the chat. Okay. Either way, okay, so we have gas as like a way to meter resources, and that's because otherwise, right, there's like obvious ways to attack the network. Okay, and then here's bytecode, here's EVM bytecode and things that it does. Okay, so I realized I just probably threw a lot of jargon at you, and I probably was too much, but I want to now look at, for example, an actual ETH transaction that I just, this was hours ago that I found, and you can kind of see some of the stuff I'm talking about. So, oh, not that one. Not that either. We'll just click the link. Okay, so here's what I found. This was, what, 2.5 hours ago. And it was basically an ETH transaction, not to a smart contract, but just an ETH transfer. It might not be super clear, but basically there would be bytecode attached if it were the other type of transaction. And we can see it's like, the transaction says transfer 9.8 ETH from this address here to this next address. And someone has gone and like figured out that this is actually an address belonging to this exchange. So this is like someone withdrawing Ether from an exchange. So like I could go and like, let's say I want to like buy some ETH. One way I could do that is I go and deposit my dollars into some exchange. Like I've never used crypto.com, but let's say crypto.com. I trade whatever the ETH price is, here, $368 for 1 ETH, and then I like want to withdraw my ETH, right? Here's the gas I was talking about. So, oh, that's interesting. So a simple ETH transfer, so just moving ETH, is the cheapest, or it's the lowest amount of gas that you can sort of do in terms of transactions on the network. And so that's 21,000. There's like, no matter the transaction, there's this base cost of 21,000. They set a gas limit for much higher, which is a little weird, but you can do that.
Does that correspond to an opcode? Because I see one GTX costs 21,000 gas. Does that correspond? Sorry, I'm just confused.
No, yeah. Let's clarify. So it doesn't. I wouldn't say it corresponds to an opcode. What it means is that. So okay, this isn't a great example because. And this is what I meant earlier when I said that the ETH transfers are like kind of hard coded into the protocol. You can imagine there being EVM bytecode to do these things, but because this is such a common like special case of like moving the base currency, that it's basically hard coded in, and it's like it lives outside the EVM within the client.
Oh, okay, I see.
Yeah, but still, so this is when you make it, whoever made this transaction, they did say they specified from, they specified to, how much value, like in this case, how much ether whipped in. There was a transaction fee, which they ended up setting via the gas price. So they picked the gas price because you could, again, because there's like essentially an auction for block space, this gas price moves all over the place. They picked that gas price of 29 gigaway. And because this was a simple ETH transfer, it used this much gas. So what that meant then is that they paid this much gas times this price, right? And then that's how you get to this transaction fee. Does that make sense?
Yeah, I think so.
Okay, yeah, just multiplying gas used by the gas price. And then you end up with like units of Wei, which again is just like a denomination of ether. So I realize I'm running a little bit behind, but to give you a little, well, here, let me see.
It's okay if you run over a little bit, that's fine.
Oh, okay.
We typically do.
Oh, okay, good. So let's see what's behind here. Because yeah, no, I want to give you intuition for, well, okay, yeah, that's where we're going next. This was the simple ETH transfer was the first one. And then now this is the other type of transaction that is a smart contract interaction. And again, what this means is that what we're doing is we are, someone has deployed some EVM bytecode at this address, in fact, for this transaction. And it turns out that this is for this protocol called Aave, which is essentially, so it says lending pool. This is, if you've heard of Compound, or also a little bit like MakerDAO, but basically it's like a money market. And so what that means is basically, if I have some extra capital lying around, like let's say I have a bunch of dollars, I could like lend them out to someone. Like let's say I have more dollars than I need, I could put them in this market, and then someone who needs them for some amount of time, they could actually borrow them from me, right? And there's an interest rate, right? So I get some yield for like providing this resource, and then they're consuming the resource, and then there's again compensation for that fact. But either way, Aave is this money market protocol, and I've not looked at the Aave smart contracts. We could. I was actually going to have us go look at Uniswap in a second. But either way, like the point being, actually, what happens if we go here? So now this is Etherscan, by the way. So it's it's again very popular block explorer for Ethereum, and you can see there's all these transactions. These are all pending because people want to do things against Aave, like basically borrow or supply assets. But okay. So just because you asked in particular, here's like, okay. Apologies if this isn't very helpful, but it's kind of what you asked, which is I want to see the bytecode for the transaction, and so, or for the contract. So there was a transaction, right? This is where we started here on this page. Someone, whoever 24A, blah, 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 whoever this is, right? They broadcasted a transaction that was to this address. And it just happens that this address, if we click on it, is a contract, which means that it has bytecode stored on chain. And we can go look at that bytecode, again, because it's a contract, it's indexed here. And it turns out that actually, because this is actually a very popular contract, they've actually gone and like linked the source code, the Solidity source code, which again, we're going to get to in just a second. But anyways, what happens is the Solidity source code is compiled down to EVM bytecode that we were just talking about. And basically this is it. This thing I've highlighted here. Again, this is a hex encoding, right? So it's just like a bunch of base 16 numbers for like the code. So just like you could like compile a C program and you get out some binary, this is the same thing for the EVM.
Yeah, so like you said before, this is just a program, and the input is the transaction or the Ethereum that they sent, right?
Right. So there's a few subtleties that I'm probably going to gloss over because I don't think they're that helpful for this. But basically, this blob is executed and produces the contract code. And then what happens is when this transaction is executed, it includes, actually we can see, okay, so what it does is basically say, the way I would do this, like if I wrote it manually, I would say, I want to, okay, so I say it's from me to this contract. I want to include 0 ETH. I want to set a gas price of 27 gigaway. And there's some input data, right? There's there's like a transaction payload attached. And let's see. One way to look at it is like this. So it's literally just these bytes, right? It's just in hexacoding these bytes. It turns out that there's like a sort of convention that we all use, that Solidity uses at least, in terms of how you interpret those bytes. And so what happens is that, okay, so the way it works is that, sorry, I'm jumping around, but basically you go, if you want to call, say, well, I'm not going to find it. Here, let's say I want to call get token distributor. I basically hash this function signature and take the first 4 bytes, and that is what we're going to call this method ID. And so basically what that means is you take that, you literally just like type this, you hash it, you take the first 4 bytes. That's what this is. You then encode the parameters to this thing in a certain way, and then that's how you end up building this transaction data, right? So you see here, the first 4 bytes here are, let's see, 1, 2, 3, 1, 2. This basically then, what happens is this is executed in the context of the contract. It says, okay, I'm going to dispatch on these first 4 bytes, and then basically it's a pointer into the compiled code. It's then going to know how to read off these arguments, and then it's going to execute. And I jumped ahead a bit, so let's go take a step back and look at Solidity a little more closely. And I think what I said will make more sense to everyone. Because yeah, otherwise I'll get ahead of myself.
And maybe perhaps just a high level, just what the flow is. When did the contract went on the chain? What does it mean to invoke that contract? What does it mean to send those parameters? And
sure.
So just a high level flow. That would be very nice.
Yeah, so the way that this would have worked, the way that this would have happened, I mean, again, it's all public, so we can look, but basically, Aave, like, the Aave team wrote these contracts, and again, a lot of this is like well-known library code that everyone uses. A big bit that I'm probably not going to have time to get into is like smart contract security. The takeaway is that it's very important and it's really hard to do. But basically, there's some like very well audited code here, so why not reuse it? And essentially, you write these contracts. Okay, so you see there's actually a good bit of source code here, but this is like implementing the Aave protocol. So you write the contracts, you would compile them down to EVM, and then I might have to, let's see. Oh, here it is. So what happened was someone else, allegedly the Aave creators, right? They basically made this contract via this transaction. And so we can see that, I mean, it'll be in here. Oh. What? Creator. But that is not the right transaction. Either way, the person who made this contract deployed, well, they broadcasted, might be a little more precise, they broadcasted a transaction with this as the data, right? So whereas before, this was our data to execute this borrow function. We wrote, this is the payload. Whoever deployed the contract wrote this whole thing as a payload. And that's because this is actually executed, and then the thing that's returned from this is the code that's stored on chain. And then that happened. Okay, so the thing that I'm coming back to here, so this should be the transaction that deployed it, but I'm a little confused because this is the same. Oh, I see. Okay, so this is actually, okay, that's confusing. What it's saying here is basically that some property was, oh wait, Okay, I think this is what I was looking for. It was just, I think there was a step of indirection. So the person who deployed the Aave contracts was, effectively using this address. And now this makes more sense because it's a contract creation. And again, like I said, the payload is like this huge blob because that's the source code for the contract, right? And you can see that, it took a bunch of gas, 1.5 million gas, which is like actually a lot. They paid 15 gigaway, so it was not that expensive to deploy, which is good. But yeah, so they deployed this contract, and then as of block, 9.24 million, is that right? Yeah, 9.24 million. This has just been living on the Ethereum blockchain. Sometime much, much later, block one, what is this, 11 million? Yeah, so 2 million blocks later, roughly, someone came in, they decided they wanted to borrow 20,000 of TUSD, which is just another stable coin. And so the way that they did that is they issued this transaction that worked against that smart contract. Is that helpful? did I confuse more than otherwise?
No, I think it was really good. I just wanted to kind of everybody hear that broader context in case they're not familiar with it. But I think that was excellent.
Okay, great. So we might be able to skip some of these slides. Again, like I said, I got a little ahead of myself. I got excited, but it basically, so EVM is like very low level, right? So like to give you a very painful example, like none of us would want to sit and like write this bytecode, right? Like you wouldn't want to sit and like write these bits somewhere like that. It would just be silly. I know people who have done it. I mentioned security. Something you can do is use this technique called formal verification, where basically what you want to do is write mathematical proofs and then show a correspondence between properties of the proofs and theorems about the context with the actual bytecode. And so you can apply formal verification against the Solidity source. It turns out then there could be like bugs in the compiler that like are not good. And so if you really want to be sort of secure, you actually do formal verification against the bytecode itself. And so like, for example, we've done that with the deposit contract, which is like a really key piece of the ETH2 infrastructure. You can ask Preston about that. But anyway, it's it's a very, very detailed undertaking to do this. And anyway, the point being is that no one wants to write this by hand. And so what you do is what we do, in any other programming context, right? You write a higher level language. So for example, you don't want to write like, again, into assembly, you want to write like Python, right? Because it's, if you don't have to care about these details, then like let the computer, pick them for you. So that's the idea here, is that there's a few different high level languages that target the EVM. The one that pretty much everyone uses is Solidity. And that's going to walk through some code now. So, Solidity was kind of meant to be like an analog or like familiar thing to C++, to like JavaScript, Java, that family of things. Here's the syntax for like making a contract with name C. Sort of if you're again familiar with Python, let's say, it's like you could think class C. You have a function is named F, and it takes two integers, A and B. They return an integer, public and view. These are modifiers about sort of permissions to this function, which we can go into if you'd like, but essentially, sorry, they're here. And then this function is pretty simple. It just says return A times the value of B plus 42 plus the block timestamp. And this is kind of like a magic variable, but the idea is every block has a timestamp. So that's, where these timestamps are coming from here. Let's see. Yeah, here's a block. This is, and again, there's like a nice UI for Etherscan, but basically there's a Unix timestamp written into the block. And so you could actually reference that at runtime via this block dot timestamp syntax. And so, anyway, there's a number of reasons you could use a timestamp. Here, it's just kind of a toy example. And again, this came from the Solidity docs. They're very good. If you want to, roll up your sleeves and start writing smart contracts, read the docs. Maybe that's not that helpful, but useful if you sit down and read them. So here's an example C, as in the contract C. And okay, so now we'll move to a slightly more complicated example, and this is using this Remix IDE. This is actually something maintained by a team at the Ethereum Foundation, and it's basically Solidity compiler and like this whole runtime inside the browser, right? So that's pretty handy. It's like written in JavaScript, so it's here in the browser, ready for us to use. So just toss this together, just before this call, but essentially, we have a contract. We can store this variable X, and I'll talk in a second about the fact that this is, well, maybe I'll talk now. So essentially this X is, the fact that this is here, if you see this in like, again, let's say Python or Java, like this is called like a class variable or something like that. Here, what it means is that when we deploy this contract to the Ethereum blockchain, there's going to be reserved a spot for it in the state for this variable X. So that will mean that you can basically say, given the Ethereum state, go to a particular address, and that's going to have this bytecode. It will also have a commitment to the state of this instance of this contract, which will contain, a space for this integer variable X. And what that means then is that now we have these functions to set X and get X. And again, they're really simple, just write or read the value of X. And, but what this would actually mean is that if you wanted to, you could then turn around, you make your own transaction that, in form and function, it looks exactly like this. You go and write your own transaction, and you could, for example, call set X, and you would say, okay, I take the function signature and I hash it, and that gives me this method ID, and then I like encode the value X that I want to write, and then I broadcast the transaction that's then executed by the EVM, which says, okay, I need to go read the contract state. I see then that it sets this value to X, which is the storage into memory. This essentially all boils down to over here what we're going to call S load, which is storage load. And that's because, there's a chat. Okay, so someone asked, do we need to buy the gas with the fiat currency? And so you can only pay for gas with Ether. Sorry, that was a distraction. I got sidetracked. But essentially, you can only pay with Ether. And yeah, you can't say like use dollars to buy for gas. You could trade your dollars for Ether, right? And you have ETH to pay for gas. But basically, gas has to be paid in ETH. Back to the smart contract. Sorry, I just got distracted by the question. Back to the smart contract, right? You would do your S load to, well, actually, sorry, it would be S store. I told you the wrong one. Where is S store? Oh, see, I think this is a little outdated. But anyways, there's basically an opcode to write to the state. The reason I point this out is that like if you ask, today what's the bottleneck to Ethereum, it's actually the size of the state. And so it's like, something that we all as developers of Ethereum worry about a lot. Either way, read and write to the state. And okay. So with Remix, you can actually deploy the contract. It's like an emulation of what would happen on the blockchain. So we're going to do that. So we deploy the contract. We see now it's deployed here. We can say set X. So let's set it to like 234. I don't know, I type some numbers. And then we see, oh, like actually there was a transaction, right? This is, okay, this is very tiny. That's a little better. But basically, just like we saw in Etherscan, right? There's a transaction hash. It was from some address we made up in the browser, right? Over here, you can see there's just like, this is again a test environment. And we called the C contract, the method set X. with the value that is down below. You know, we set a gas limit. It costs 41,000 gas to execute. Oh no, sorry. Oh, interesting. Okay, so the total cost was 41,000. See, this is like some debug information. But either way, the input is here, and the output we get back actually might not be anything because we're not returning anything. But what we can do is we can say get X, and we have another execution, and it turns out that we get back our value. Okay. Did that make sense to everyone? Sorry, I know I jumped around a little bit.
No, I think that was excellent. That was the first hands-on, I guess, using the IDE as well. So no, that was perfect.
Yeah. Remix. Yeah, this is handy. I've actually like developed and debugged contracts in here. A lot of, so like you know, and you'll probably get a sense of more of this next session. Well, maybe not, but either way, a lot of the tooling around this stuff, because again, it's also new, is like very immature. And so, you know, you might not have like the nice fancy tools you're used to in say like JavaScript land or like something like this. But yeah, I've literally like sat here and like tried to like debug contracts, just because it's like a handy sort of compile, debug, sort of execute loop, outside of what I may have had otherwise. So, okay.
So I think this has been just superbly exciting, and I mean, I wish we could just spend a few more hours talking about it, and
yeah,
just
okay.
an excellent speaker
Sorry,
as well.
I ran out of time.
But maybe we can, so maybe in the next 2-3 minutes, we can wrap up. You had some really important points on the security. Let's kind of touch upon the security points that you have.
Sure.
I think that would be a really nice conclusion.
Yep. So I will, let's just zoom through the rest of what I had. We made it most of the way there. I hope this is helpful to everyone. Basically, I was then going to look at an ERC20 contract, and almost certainly you'll get these slides. I mean, I'll go post them online after, so you'll be able to find them. This was like, because again, you'll hear ERC20, like people are all about the tokens. So I was going to walk through like actual token implementation. And so just really quickly, you see, here's a Solidity contract. You know, we're going to call it an ERC20. And this happens to be the interface, right? That the token, you know, this contract implements this token interface. There's like some private variables, which basically maintain balances of the token. And, you know, just to give you a really brief example, okay, so, you know, you could say, what's my balance? You know, what's like the balance of this address for this token? And you literally just like look it up in this map that we have. You could say transfer, which calls to this helper function under bar transfer, which is here, right? And it basically says, I mean, the important bits are really as simple as this, is you say, okay, the sender's balance is going to be less what they had, and the recipient's balance will be more than what they had, right? You by the amount. And if you think about it, again, we're gonna have to blow through this, but basically it, you know, it's moving numbers around on a spreadsheet at the end of the day, as they say, and now we have token contracts. Okay, so again, obviously we didn't go fast enough, but I was gonna look then at Uniswap, which is a centralized exchange. I'll just let you dig into this at your own preference. Security. So like I was saying, everything is super immature. Again, like this is, you know, this is actual value. Like people, you know, we've made these systems, they seem secure enough. They are secure enough that people, here, let's just go take a peek. People are willing to put, you know, billions of dollars, you know, into these networks. So, you know, just kind of roughly looking at market cap, you know, the market cap of Ethereum is like, what, 42 billion? So people trust the network enough to like, well, and this is only the ETH market cap, right? So anyways, the value hosted by this thing is like, actually like, it's ridiculous. And so what that means though, is that there's real value at stake, right? It's like, I could put my life savings into some random smart contract. And again, I didn't quite get to like a more, like I was gonna look at Uniswap because it's like, here's just a quick peek. It's like, you know, you can see there's a lot more going on. And there's, you know, it gets to be a lot of code. And so now you have like the problems you usually have with software, which is that it gets too complex, too fast. And inevitably bugs fall out, right? And so the thing is though, now it's not that just like, oh, like my food delivery app is going to bring me tacos instead of, curry, what's going to happen is that I'm going to lose like my life savings. So again, hopefully I've transmitted some of the excitement to the space, and like, you see, at least you at least may vaguely understand that there's actually something really like novel and interesting here. But I do want to hammer home this point that like, this is actual value. People are putting the real, like, actual, hard-earned dollars into this stuff, and it's easy to lose. It'll probably always be this case just because like bugs happen. But even just given where we are today, we don't have, like, for example, in traditional finance, you would have like insurance and like, facilities like this to like hedge some of the risk. We basically have none of that in DeFi example. And so like, there just isn't, there's not a backstop, right? It's the Wild West, and it's super exciting, but that means that there's a lot of risk, and moreover that you are very directly taking on that risk. So the point is, be careful, definitely be careful. Read the code of the contracts that you see. Testing. We'll come back to this. Again, very exciting, but high risk. I mentioned formal verification and like audits. And again, there's like, things that we do to try to make sure that you have secure contracts. But yeah, it's, bugs happen, and it's early days. So yeah, I was going to walk through the DAO hack and like kind of how this would work, but again, we ran out of time. It's here in the slides. I mean, I'm happy to like chat individually if anyone wants to, so keep that in mind. Yeah, we might be out of time for questions, but again, here's my Twitter handle. Like, feel free to DM me. Like, I'm here.
All right, Alex, thank you so much. That was a amazing talk, and yeah, just thank you so much. And I'll definitely get the recording and post it on the website, along the slides, and of course your contact. And if you student have any question, we'll definitely direct it towards you. But again, on the behalf of the whole class and UC Davis, I think thank you so much for coming and attending, and it was really nice. Thank you so much.
Great, yeah, I'm glad I could help, and hopefully all of you got something out of my rambling and my ranting. A lot of cool stuff going on. So yeah, I'll
thank
see
you
you
so
around.
much. All right, thank you very much, everybody. Thank you.
Bye.